Work or project. The purpose of this lecture is simply to give you a sense of the types of research and recent work that people think about when they do machine learning research or applications of machine learning into other types of research projects. And we'll look into sort of two applications, edge detection and speech animation. Let's see. Okay, and just one more announcement. There's some more seats over there. There's a few more seats over on that side. Recitations, the remaining recitations will be moved to Tuesdays. There's two more recitations, one on probability and one on dynamic programming. And because it seems like the majority of students attend office hours on Thursday nights, which currently conflicts with the previous recitations schedule, all the recitations from now on will be on Thursday evenings.
Wait, recitations?
So, excuse me, Tuesday evenings. Sorry. Okay, so today we'll be talking about two applications, one on edge detection, one on speech animation, and then I'll close with a little introduction to this concept called learning reductions. Okay, so let's start with edge detection. So edge detection is the problem where you're given an image, let's say in this case X, here we see three images, find the edges of the image, so that's given here in the Y's. And for simplicity, we'll assume the supervised learning setting where we're given annotations. So someone has carefully annotated the edges of these images. So we have this supervised training set, right? And the goal is to find a mapping, a function, a classifier, well, it's a little bit more complicated than a simple classifier, but some sort of mapping that maps this type of X to these types of Y, right? Okay, so obviously this is not just a very simple classification or regression problem. The output space here, right, is a space of black and white pixel maps, right, or grayscale pixel maps, right? So for a 400 by 300 image, which is what this is, there are 120,000 pixels. So if you want to actually predict in this output space, you have to predict over 120,000 numbers. Right. So if one were to be super naive about it and assume that each pixel can be black or white, on or off, that's a huge label space, right? So obviously, the super naive way of thinking about predicting in this space doesn't quite scale. And today we'll be looking at different ways of reducing some prediction problem, or consequently some learning problem for that prediction problem, into something that is simpler for us to solve, right? And so the basic idea is we convert some complicated problem into a simpler one, or a set or sequence of simpler ones, and then we use and then we can use some of the very advanced machine learning methods that we've covered in class on this simpler problem, right? Such as decision trees, random forests, and neural nets. And then we recompose the predictions back into the complicated space. Right? So that's sort of the idea. And so what are some observations we can make about the edge detection space that can help us reduce the complexity of the prediction task? One of the very important ones, and we of course covered this in a different context with convolutional neural nets in the previous lecture, is the fact that images contain strong local properties, right? So it's the local patterns that match. For example, the image patches, right? So for example, if we want to do edge detection in this space right here, right? We can more or less assume that we only need to look in this neighborhood, right? The predicting the edges of of this part of the image has a very weak, if any, dependency on what's going on over here in the image, right? And so we can make the assumption that edge detection is a localized problem. We can just sort of look at the neighborhood of this particular part of the prediction we're trying to make in order to make a pretty good prediction. Of course, the relationship can be highly complicated, right? What exactly makes this an edge, right? This part an edge, whereas this part is not an edge. What defines what is an edge, what is not an edge is a very complicated relationship. So within this local neighborhood, things can get very complicated. You could just think of this as sort of like a global property, right? That says let's figure out how to model the neighborhoods really well, and we can forget about modeling dependencies that are that lie way outside of this local neighborhood. That's sort of just a global structural property that we can assume, and I'll show you how to formalize this property into a reduction in a few slides, right? And so, well, actually in the next slide. So we're going to do a sliding window approach. And so here the idea is that we're going to train a model to predict patches of edge detections. In this case, in this particular example, 16 by 16. So we're going to train a single model that can make 16 by 16 predictions, which is much less complicated, right, than 400 by 300. And then we're simply going to slide this prediction across the image, right? So we're going to take the patch predictor that predicts in this localized window and simply slide it across the image, right? And so now the question is, okay, what do we use to make predictions in this 16 by 16 patch? And the answer is basically almost anything, right? You could use, if you had the right features, an SVM. Right now we're going to talk about decision trees. You can use neural nets. It's sort of, all we care about is some machine learning algorithm that can predict well on 16, in this case, 16 by 16 image patches that then we could slide across. Right. And so just a reminder of decision tree, which I hope you're all sick of by now after homework 3, is simply a nonlinear function class that that defines these nonlinearities through these hyperplanes, axis-aligned hyperplanes that cut through, that recursively partition the space of functions until you get sort of a piecewise static function class defined by the leaf nodes. Right. Of course, this is a binary. This decision tree predicts zeros or ones, right, at the output nodes, and in fact, all of the prediction tasks that we've looked at these days in this class so far makes predictions in terms of a single number, right? Binary classification, we make prediction in terms of a single number. Regression, we make predictions in terms of a single number. Right? Here we need to make predictions over 256 numbers, right? If it's a 16 by 16 patch that we're predicting. Right? And that leads to what's called a structured decision tree. Right? And I should mention that there are a few different ways that one could go about doing this. I'm just presenting one approach. There are others that you can imagine. And as always in research, the verdict is still out in terms of what ends up being most useful, but I'm just here presenting one approach. And so here, each leaf node predicts a 16 by 16 edge matrix, right? And how you define this 16 by 16 edge matrix is the average of all the training patch labels, right? So if you recall, when you train a decision tree, right, it defines a partitioning over the training set, right? And then the predictions you make at each leaf node is then some kind of averaging or aggregation of the labels, of the supervised labels of the training examples that got partitioned to this leaf node. And so here, if we had some way of constructing such a partitioning, then every leaf node is basically a collection of 16 by 16 image patches with their supervised label, right? And we'll just simply predict the average label of all the training patches, right? And this prediction is very fast, right? We can slide the predictor across the image and then average results. We don't need any kind of dynamic programming, which if you're not familiar with, we'll get into in gruesome detail at the end of this course. And in fact, because it's a sliding window predictor, it's embarrassingly parallel, right? You could even instantiate the predictor multiple times, slide over different parts of the image in parallel if you have a multi-core machine, and so it parallelizes trivially, right? The only thing that remains in terms of this particular setup is to define a splitting criterion. What is the set of query functions that we should use to actually how do we define the impurity measure, right? That we can use in order to decide how to split, and of course also the query set as well, right? So at this point, before I talk about the definition of the impurity measure and the definition of the query set, assuming that we have such a tree and we have these predictions, is that clear? Any questions on the setup so far?
Did the edges from one of the 16 by 16 patches depend on any edges on nearby patches?
They might, right? So, you know, if two image patches are very similar, then it is likely that they will get partitioned into, well, the probability is reasonably high that they'll get partitioned into the same leaf node. And so it is up to the impurity measure and the query set to capture relevant statistics of edge detection, of the edge detection problem as it relates to pixels, input pixels, such that, you know, related image patches with similar looking edges in the patch get partitioned into the same leaf node. So it's sort of, so as long as you define that family of query sets and impurity measures correctly, the data will speak for itself. Okay, so let's first talk about the impurity measure. By the way, this is I'm describing a paper that was published a few years ago. It's called Structured Random Forests for Fast Edge Detection. It was published at the International Conference for Computer Vision about 4.5 years ago. And so let's talk about structured information gain. So here, recall that we're in the supervised setting, right? And we're not talking about the query set yet. So let's just suppose that we had two different types of, we tried two different types of queries. We have, in this case, 12 examples in this current node, and we're trying to figure out how to split this node to reduce some impurity measure, right? And here we have two different queries that it results in two different splits of the training data. And here I'm only going to look at the labels because the impurity measure only looks at the labels. The query function only looks at the inputs. The impurity function only looks at the labels, right? And so here I'm just looking at the labels. So you get these edge patches, right? And so, you know, the query function that we chose on the left split the training data into these two leaf nodes, right? And, you know, just from eyeballing it, I think we can all agree that this is a pretty good split, right? Like these edges all look very similar, and these edges all look pretty similar, right? Whereas the query over here, on the right, it split the training data into these two partitions. And I think we can agree that this partitioning is pretty bad, at least certainly bad relative to the partitioning we get on the left, right? And so the question is, how do we formalize this? How do we rigorously define a definition of information gain that captures this intuition? Okay, so here is the idea that the authors of this paper proposed. What I'm presenting is going to be a simplification of their idea. What they actually implemented was a bit more complicated, but I think this simplification captures the high-level idea well. Yes.
This is a sidebar, but I noticed in the images, it looks like it's not one boundary around the face, but it's sort of like several thinner boundaries overlaid.
That's right. So what they ended up doing, this particular approach, and again, you know, there's no universal right answer. What the authors of this paper ended up choosing to do is to predict in grayscale, right? So you get these sort of a little bit blurred boundaries, and you know, there are trade-offs there. You get in some ways a more robust prediction, right? In the paper itself, they had some post-processing heuristic to sharpen the image, the output prediction. You know, there are trade-offs there. So here, just for simplicity, we're going to allow ourselves to predict grayscale images, grayscale edge maps, and so it's going to be a little bit blurry. Okay, so here's the type of structured information gain that the authors proposed. So first, we're going to map the labels onto a coordinate system, right? So imagine that we're going to map labels onto, you know, like let's say 1,000-dimensional vector, right? And each coordinate corresponds to a pair of pixels, right? Recall that the image patches are all the same size, 16 by 16. And so for every coordinate, we're going to choose a pair of pixels, let's say at random, right? And we're going to set this coordinate to 1 if this pair of pixels, right, are in the same segment as defined by the labels, right? And we're going to set it to 0 otherwise. So in this particular example, let's say the first coordinate corresponded to these the first coordinate in this feature space we're going to create, or vector space we're going to create, corresponds to these two pair of pixels, right? And for this particular image patch, in terms of the labels, these two pixels do not correspond to the same patch, right? There's a boundary, there's an edge boundary that separates these two pixels, so we're going to set the coordinate value to be 0. Okay? And then let's say coordinate 2, the second coordinate, corresponds to these two random pairs of pixels, right? And in this particular image patch with these edge labels, these two pixels belong to the same image patch, right? And so we're going to set that coordinate to 1. And we're going to just repeat this process, for let's say 1,000, 5,000, 10,000 times. And there are certain details here, like what is the randomness of this distribution? Should it be locality sensitive? Should it be uniformly at random? These are all sort of issues I'm not going to go into, but that's this sort of the high level idea, right? And we're gonna have the same sort of mapping of coordinate to pairs of pixels for over all possible training patches, and we're going to simply generate this coordinate, this basically vector representation for every training image patch, right? And then we'll cluster the training labels using this coordinate system. And so this gives us a representation. This gives us a representation of similarity, right, between image patches, as represented by whether or not they two pairs of training edge patches. Do they agree? How often do they agree on whether or not a pair of pixels belong to the same patch or not? Right. That's basically what this is defining. Any questions on that? Yes.
For part 1, part B, did they do that by hand, or do they already have the edges?
There is an, right, so this is a supervised learning setting, so we assume that we're given a supervised training set where all the images have their edges labeled. And so from that, you can, there's fairly simple algorithms that can basically color code the segments of the image patch, and then when you look at a pair of pixels, you just check if they're the same patch ID. It's the algorithm is pretty simple. You say this is patch 1, and then you just sort of diffuse it until you hit a boundary, and then you're done, and then you terminate, and then it's right for a search. Yeah. Any other questions? Yes?
Wait, but then if you have that, then does a human define where the boundaries are, or like what pixel color differences you have to have?
No, that we're going to learn that.
Oh, okay.
Yeah, that's what the learning algorithm. All the human does is provide the edges, right? Draws the edges of these images. The mapping from images to edges is what the machine learning algorithm is going to do. Yes?
Are you clustering the training labels so you can figure out if two image patches are or are not in the same cluster, or could you just use like a distance in between them?
You could. They chose to do clustering, I think, just to do another round of dimensionality reduction. Yeah. So we're going to get to that in the next slide. Right. By clustering, right, we've reduced the training labels to membership to one of k clusters. Right. And we'll talk about, for those of you who aren't super familiar with clustering, we'll get to that next week. It's literally what it sounds like. We're going to group the data points into k clusters as measured by similarity in this coordinate system. Right? And so by clustering, we've reduced the label space, the complexity of the label space, into membership in one of k clusters. Right? And once you've done that, you can use standard impurity measures like entropy. Right? We covered entropy for the 2-class setting, right? Plus, when the label is 1 or -1, as the entropy of the distribution of what fraction of the training examples are class 1 versus class -1 or class 0. There's a very standard multi-class generalization of entropy, which is you could do it over any multinomial distribution, right? In this case, it's k classes rather than 2, and the entropy definition extends in a very straightforward way, right? And so in some sense, we're just treating this like multi-class classification. And the impurity measure is a multi-class entropy, right? And so, you know, in this case, you know, here we have k equals 2. In general, k is much larger than 2, maybe like 20 or more. And here k equals 2, and so, you know, we've clustered the image patches, the edges, into these two clusters, and you know, in this case, in this idealized example, they're clustered according to the way that we expect, right? The blue ones all look very similar to each other, and the orange ones all look very similar to each other, and hopefully that will follow through based on this idea of, you know, the blue ones all share more pairwise pixel patch memberships, right? Agreements than they do with the orange ones, and vice versa. And so, you know, the goal is to then find a query that improves the impurity, right, of the resulting partition. And that's the impurity measure. Any questions on that? So I will make a comment. You know, this seems very complicated compared to all the things that we've talked about in class so far. And that's because the real world is complicated. You know, in the first 4 weeks, we've mostly talked about very simplified, abstract learning models that form the foundation, the core of machine learning. And this particular application where people are trying to get it to work in the real world, you see that we have all sorts of high-dimensional structured problems and trying to find reductions of these complicated problems into something that we know how to do as we learn in class is part of the challenge of getting machine learning to work in practice. But, you know, in this formulation, now we can solve it using a standard decision tree learning package. Right. Okay. So now let's move on to the query set. We've defined the impurity measure. Now we need to define a query set, and then we can do decision tree learning, right? And the query set is, at a conceptual level, it's pretty straightforward. They just use standard, you know, image features like gradients and color maps and convolutions and stuff like that. So there's not really much to talk about in terms of the low-level details. It's simply the standard image features that they use. They simply, if there's some color gradient from this part of the image to this part of the image that matches some color gradient in some other patch, then they would both get partitioned into the same partition, sub-partition. And these days, you know, if you wanted to, you could use the feature representation that's the output of some convolutional neural net, if you wanted to. And so putting it all together, right, we create this new training set. So we have this old training set, which was 400 by 300 images, and a 400 by 300 edge map supervised label. We're going to create a new training set of 16 by 16 images and 16 by 16 ground truth edge labels, right? And so we chop up this big image into smaller ones. Of course, we have lots of big images, so we chop up each of those into smaller ones. We combine them all together to form this new training set. And then we train this structured decision tree on this training set. And then we predict by sliding this decision tree over the input image, and then we average the predictions, which will, of course, blur the predictions out a little bit. And as you can see here, they don't actually use a single decision tree. They use also random forests, right? So you can apply the whole random forest methodology to this problem. So let's look at some results. So here are 5 results. Might be a little hard to see. So the ground truth is a little bit hard to see because of the resolution of the, or contrast / resolution of the projector. But here are the 4 different versions of the method. right? And it looks pretty good. I mean, it's a little bit blurry, right? But overall, it looks pretty good. I would say that this looks very good. Yes?
Is this method better in any way than the traditional means of edge detection in images?
I'm sorry, traditional what?
Traditional methods of edge detection in images.
Yeah, so let's talk about a comparison with the state of the art, or the state of the art at that time. Obviously, there have been improvements since this, but in terms of performance, it's comparable to the state of the art, right? In terms of running time, it's this is a single tree. This is a single tree. This is a 4 trees. It's about a factor of 1,000 faster. Yes.
What are the 3 accuracy measures?
I'm sorry, I
What
can't.
are the 3 accuracy measures?
This is average precision, OIS. OIS. So, okay, without going into exactly what these might be, because I don't remember, at a high level, when you do these types of prediction tasks, you could over segment, you can under segment, you could be off by a little bit, right? So, here's the if that's the ground truth, right? And we get, and then we might be over segmenting or under segmenting, right? And so there are different ways of measuring what you penalize more or less, right? And so without going into without describing exactly what these are, because I don't remember what they stand for, these are, depending on what you care about more, you can define a different accuracy measure. Like sometimes you care about, sometimes you would rather over segment a little bit more, as long as you got all the segmentations. And for some applications, you only care about the really most important segments, and then you don't care about the finer grained segmentations. And that leads to some asymmetry compared to just straight up accuracy. Any other questions? Yes.
Is there some deeper message to take from the fact that these 2 very different methods are achieving, by these measures, like almost identical performance or accuracy?
I wouldn't read too much into it.
Well, I ask because it seems suspicious to me.
So, I've been doing research for about 13 years now, and I understand a little bit about a researcher's psychology. They may have just tried enough just to be competitive with the state of the art, because what they cared about, as you see in the title of the paper, right? They really care about fast, right? And so, in terms of just sort of having an elevator pitch for what this paper does, it's much easier to say we're exactly at the state of the art and we're 1,000 times faster than actually we're 5% worse than the state of the art, but we're 1,000 times faster. And if that's sort of the main message of the paper, one might question, okay, how much effort is it worth trying to get a little bit better than the state of the art? And I'm not saying that these people did that. I might have if I was in their position, right? And so, because of a variety of issues in terms of the cost-benefit trade-off, time investment in order to get a certain type of performance, I would not personally read too much into the fact that these 2 numbers are very similar. Maybe it's a fundamental limitation of this data set. Maybe, right? It's just inherently this is the best we can do. I'm skeptical that would be the correct explanation. Yeah. Yes.
So the human is at 80%. Is it better to go above 80?
So that is I would not put too much emphasis on that. It's probably someone they pay to do this task manually.
Are they lazy and made mistakes?
Yeah, it's how I would interpret the top row is what a reasonably motivated human might do. Yeah. Again, with these sort of research results, you have to take everything with a grain of salt. Yeah. Yes.
I was wondering, how did are the state-of-the-art methods that they're comparing to, are those not machine learning based methods?
Some of them are. Some of them are probably based on what do these things even stand for? Some of them are probably based on integer programming and dynamic programming and the various sorts of optimization problems, various flavors of optimization problems.
So they was more intensive that they can like actually go pixel by pixel and find edges.
Yeah, they
Okay.
like they're probably running some graph algorithm.
Okay.
Right, if you define a neighborhood graph over pixels, they're probably running some graph algorithm to get consensus,
Okay.
which can be very expensive. Now I have some second thoughts about posting this lecture on YouTube for authors. I'm not saying that, I'm saying I might be motivated to do that. Okay, any other questions before I move on to the next application?
I have a question that might be a little bit irrelevant.
Yeah.
Just like sometimes when it makes a thing that we need to fill in the reCAPTCHA to verify that we are not a robot.
Yeah.
But from this we can see that maybe from machine learning, a robot can do the same as what we do. So how could you tell that difference between robot and human?
First of all, this is a supervised learning problem, right? And so you have a large pre-collected supervised training set. Much of the reCAPTCHA technology is geared towards collecting labels where we have no supervised labels. Yeah, we're all friends. So Pyotr Dollar, the first author, is a Caltech alum, so we're all friends. Okay, speech animation, the next application. The purpose of this application is to learn to map audio inputs to lip syncing of a computer graphics face model. So basically, can we automatically animate this face model to input audio? And hopefully it works. Let me see if the sound's on. Okay, it's not on. Just give me 1 second. Let's try this again. Okay, so what I'm going to do is I'm going to just trust my laptop speakers because the audio is not working. Hopefully it's loud enough. It should be loud enough.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
So we just processed some audio by Barack Obama, and then we told our face model to lip sync to it.
Because there's never been a leak this size, at this depth, stopping it has tested the limits of human technology.
Okay, so let's talk about the training data. So what we did was this is work from my lab, by the way. What we did was we collected a training set of this particular actor. His name is Ken. We had him sit in front of a camera and speak 2,500 sentences that was recorded at 30 hertz. That's about 8 to 10 hours of recorded speech. He was a pretty tired guy at the end of the day. He was well compensated for his time. So he was more highly motivated than maybe some of those other people, humans were in the other task. This was a professional actor. And so we used standard computer graphics technology to build a model called an active appearance model of Ken's lower face. And this mouth model has about 30 degrees of freedom, right? And so here's what the training data might look like. So here's a frame-by-frame decomposition of the words X-ray vision, and here's what the mouth looks like, right? So this is the Y, and these are the X's. then the prediction task is given an input sequence X, and here we assume X has been post-processed by some speech recognition software. So X is phonetics or syllables, again at 30 hertz. And then you want to predict a sequence Y, and you can think of Y as parameterizations of our face model. So our face model has 30 degrees of freedom, like 30 knobs. You can think of it as a virtual puppet, if you will. And so we need to predict a sequence of Ys that live in this 3-dimensional space. Right? And so here's an example. Here's a frame-by-frame decomposition of the word prediction. And here I'm visualizing the first dimension out of 30 of the Y. And the first dimension corresponds to how wide open Ken's mouth is. Right? And so as Ken starts saying the word prediction, the mouth sharply opens, and then sort of slowly closes, and then holds in this configuration, and just slowly closes again. Any questions on the prediction task, or the nature of the training labels?
Why was it sampled at 30 hertz?
That was the decision of my computer graphics collaborators. I imagine that going beyond 30 hertz didn't offer much improvement. And if you go below 30 hertz, you lose some of the temporal structure of lip syncing, of lip animation. But that's just a guess. They told me 30 hertz was good. Okay, so again, this is a pretty complicated prediction task, right? And so let's think about how we can try to simplify the problem a little bit. And again, we sort of see a very similar structure that we saw in the edge detection setting. And in fact, our approach that we developed for this setting was inspired by the edge detection paper. And so first, temporal curvature can vary in seemingly arbitrary ways in a local window, right? So here it opens very sharply, other places it can be very smooth, right? And it seems to depend on sort of the neighboring context, right? On the other hand, like in edge detection, there seems to be minimal long-range dependencies across time. So what that means is, how your mouth is shaped to speak the end of the word prediction is more or less the same as the end of the words construction, election, etc. Right? And so there are minimal long-range dependencies, which again, put these two things together, it sort of motivates some kind of sliding window approach, which I'll sort of describe briefly. But just to sort of hone in on this first part, where the temporal curvature can behave seemingly arbitrarily within some local window, let's look at an example, right? So this is called co-articulation in the speech animation community. And it's the observation that the way your mouth is shaped to speak any syllable, in this case we're going to see some examples of the syllable K, is highly dependent on the neighboring syllables. This is sort of the co-articulation. So here you see a few examples. So the traditional approach that people thought of in the past, which was have some canonical shape for every vowel and then sort of do some Bezier interpolation to stitch them together, it doesn't really work because of this issue. Which is why we need a model that can really capture the local properties in a seemingly arbitrary way. Right? Oops, let's not do that. Right? And to just elaborate on the weak global properties, right? So again, we don't need to model the entire chain directly, right? We can just find a model that really nails the local predictions and then just slide it across the over time. And this motivates a sliding window approach, just like in the edge detection setting. And so this leads to the following sort of prediction task. We have an original input sequence, right? We chop it up into fixed length overlapping sliding window of inputs, just like in the edge detection case. Here, of course, the sliding window architecture is a little bit simpler because we're only sliding across one dimension, whereas in the edge detection case, we're sliding across 2 dimensions, but otherwise it's very similar. We push that through a decision tree. You could do random forest, you could do neural nets, doesn't really matter. which predicts a fixed window of outputs. Recall that our outputs, in this case length 5, are 30-dimensional, so that's 150 variables that we're predicting. So this is still a pretty complicated regression task, but it's much simpler than predicting over arbitrary timescales. Right? And then you just average to get the final output. And again, this is very fast. And this middle part is the only part that requires machine learning. Right? So what that means is, we have the original training data, variable length trajectory prediction. We chop it up into this modified training set, right, where we have fixed length inputs of length 5 in this particular example, and then you have fixed length outputs, right? And so this is what we fit to with a decision tree, random forest, or a neural net, right? And that's it. And so if we do fit a decision tree, one question is what should the query set look like? This is a regression problem. So the impurity criterion is just multivariate squared loss. So that's pretty simple. But the query is a little bit complicated, or can be. We actually worked with some linguists on this, and so we defined a query dictionary based off of phonetic features of the inputs, right? So things like, is it a long vowel? Is it a sibilant consonant, right? Or I can't even pronounce this. It's basically, does the tongue hit the roof of the mouth as you speak it, or something like that, right? And so we came up with this query set by consulting some linguists, and then that's how we used to train the tree. The full tree has about, well, the early version of this approach, the full tree has about 5,000 leaf nodes, and we actually gave the entire tree to a linguist to just look at. It's just small enough where someone who's really, really motivated can actually inspect the entire tree. Yeah. And as I mentioned before, the training loss, the impurity measure is multivariate squared loss. It's just a standard multivariate generalization of standard squared loss. So that's pretty straightforward. And then the prediction is simply taking the mean of all the target labels that partition into that leaf node. And that's the entire approach. Any questions on the approach? Yes?
So when you said sample at 30 hertz, that's the video, and then the audio sample at 45?
Audio, yeah, the audio is sampled at, the video is actually sampled at higher than 30 because it's downsampled. The representation we get is downsampled. The audio is sampled at
44.1 kilohertz.
some number of kilohertz, and it's also downsampled. Well, excuse me, it's converted into phonetics and then downsampled 30 hertz.
Okay.
Yeah.
So
Each frame
corresponds to a length of
1/30th of a second, and what is the syllable that's being enunciated. And of course there's sometimes you get some boundary issues because you can change syllables, but you just deal with that in some straightforward way. Okay, let's look at some more predictions.
Tonight, I returned from a trip to the Gulf Coast to speak with you about the battle we're waging against an oil spill that is assaulting our shores and our citizens.
Another example. Oh, technical difficulties. This is what happens when they make me update PowerPoint. The old movie format stopped working. I apologize. We'll have more videos later. Yeah. So this is the prediction for the word learning. So again, recall that dimension 1 is how wide open the mouth is, right? And so in the beginning of speaking the word learning, the mouth is closed, and then opens a bit, right? And then it tapers off. This one's for SIGGRAPH, right? Which is a graphics conference. So it closes on the GR and opens on the F, and closes somewhere. Yes?
When you're using the decision tree to get those the Y predictions, you have points and you have looks like curves or parts of that. How do you do that with the decision tree? That's not like a binary classification. What do you actually outputting out of the tree?
A real value number.
Is the-
150 row value numbers.
Is the value or the slope?
So you have a frame-by-frame decomposition, right? So you're predicting these numbers. You're not predicting the slope.
So then what's like the little line that goes through each point?
The line? This
On
line?
the above.
Oh, this? Wait, I'm confused. What's your question?
Green dot has a green line that goes through.
Oh, that just denotes the center of the center of the frame. Yeah, and it's merely an artistic thing, which I guess in this case is unintentional consequences of being confusing. Yeah. Okay, hopefully the next video works. So we did a side-by-side user study where we compared against previous approaches.
Where only one club existed before, he says two will flourish henceforth.
Let's do that again.
Where only one club existed before, he says two will flourish henceforth.
Okay, so who thinks the left one's better? Who thinks the right one is better? Good, the left one is ours. We did the side-by-side user study where we showed a bunch of people who were moderately motivated humans to judge the quality of the speech animation on the side-by-side comparisons. And so the dark bars are our approach. The higher bar means that approach won the side-by-side comparison more often. Okay. Here's a comparison with ground truth. And the audio doesn't work. I apologize. I really should. Okay. I'll just move on. If more of the audio breaks because of the new version of PowerPoint, I'll just open up the video files from my directory. So one thing that's interesting about this approach is that we can predict not just for Ken's face, who he's a lovely guy, but most people aren't really interested in animating him. And so we could actually extend the pipeline. So we can start with the input audio, right? We do standard speech recognition to convert that into phonetics. We do the animation. That's the part that I described. And then you can actually retarget that animation to some other face model, right? Not just Ken's model. And then we can import that animation into a standard editing software such as Maya, which is what all the people at Pixar and DreamWorks use, to create further stylizations of the animation, like adding smiles and so on and so forth, right? So this is actually, the whole thing is actually compatible with the existing production pipelines used for animation studios these days. And in fact, some of them are actually using this technology. So in terms of retargeting, right? So you have a reference face, and here I'm just giving you the coordinates without the textures of Ken's mouth, right? I'm going to retarget the animations to some target face, right? And so how that works, well, there's a number of different ways you can do it. There's automatic and semi-automatic and fully manual ways to do it. And basically, the manual way is what we ended up doing because it looked the best. So having a nice automatic way of doing this would be, I think, a nice follow-up work. So what happens is you have, in this case, 6 basis shapes, right? That's 6, of which you can represent all the other shapes as a linear, of which you can approximate all the other shapes of this mouth as a linear combination of, right? And then from that, you have this other face model who has a parameterization that's completely different than the parameterization of this face. And so you have an artist that manually poses each of these basis shapes in the that matches the shape of this of the reference face. I guess there's 7 because you have the neutral face, the mean face. And then after you sort of have this mapping, right, then what we can do is for any shape in the reference face, we can represent that as a linear combination of these basis shapes. And then we take that same linear combination coefficient and we apply it to this shape. And then we have a configuration of the mouth in this space. This is called a linear blunt shape deformation transform, retargeting. And so we get results that look like this.
Well, I look funny to you. I may be a chimp, but I'm dressed better than you.
I'm a PhD specializing in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organization.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português é ainda melhor, não acha?
Right, so because we're actually doing post-processing on the speech and only working in the phonetic space, the whole approach is actually language independent. So if you have an ASR technology that can map some other language to phonetics, this whole pipeline works as is. Here's one for a different language. I'm speaking Chinese here.
你们真讨厌，就坐那儿看我说话。
We can do Korean.
저는 한국어를 전혀 배우지 않았지만 이렇게 한국어로 말할 수 있습니다.
We can do singing.
Somewhere over the rainbow, way up high, and the dreams that you've dreamed of once in a lullaby.
We can map not just to virtual faces, but also to robotic faces. It's mathematically the same principle, just one's a physical robot. So this technology was deployed this past summer at Disney's Animal Kingdom in Orlando, in Pandora Land, the Navi River Ride thing, where they had those blue Navi aliens with, and their robotic faces have the lower mouth, or the lower face has 18 motors, so 18 degrees of freedom. And the geometry deformation was controlled by this algorithm.
I look forward to seeing you on Pandora. Well, not te came.
Right, so this, if you go to Orlando, you can see this robot in action. The lower face has 18 motors in it, which drives the deformation of this part of the mouth and the chin and so on and so forth. And the retarget and modulo retargeting function, the speech animation was actually driven by the algorithm that you just saw. Yes?
With the model that you had before, when you did this projection, or when you switched to this model from the high-dimensional model that you had before, I'm guessing you had to do some sort of reduction in the dimension that you were working with, given this has 18 degrees of freedom compared to...
So the retargeting is blend shapes. What that means is you have seven, so you say the mean shape. You have 7 basis poses, right? So that means I have these 7 basis poses, and I can approximately represent all possible poses in my original Ken space using a linear combination of these 7 basis poses. I'm going to have an artist, in this case if it was an Imagineer, define an analogous basis pose for each of those, and then the linear combination transfers. So that's basically how, I mean, there are other ways you can do it too. That turned out to be the simplest one. At least for now. There may be something better, but that worked pretty well for now. Yes?
So all of this is based on original training data?
Yes, that's right. You can think of Ken as sort of this intermediate language, right? Like, there's a few reasons why we chose to do that. It turns out that, under the intuition that the way we talk has more similarities than differences. And what you really want is you want a fine-grained model. You want a model that can capture the fine-grained dynamics of the mechanics of lip syncing. But whether or not your face is a little bit wider, a little bit longer, your mouth is a little bit bigger, a little bit smaller, whether you're smiling or not smiling, those are all things that you can sort of add on later, right? What's really hard for someone to manually specify is the frame-by-frame dynamics or mechanics of lip syncing. If I say ah, my mouth is open. If anyone else says ah, their mouth is open because that's how physics works, right? And so we can just learn those dynamics for a single person. We control for the variability of the speaker, we control for variability of facial expressions and so on and so forth. And then, so we've completely isolated out the mechanics of fine-grained lip syncing, and that we transfer.
Well, I was wondering what happens if you use data from more than just candidates of multiple speakers?
Well, then the retargeting becomes complicated, right?
You mean it wouldn't be able to reproduce the movement?
Well, suppose we made predictions for 2 faces, and now we want to retarget this to a 3rd face. How would you do that? You would have to find some combination of these 2 faces, right? But you know, if you learn one face really, really, really well, then you could just retarget the mechanics to another face. Now, there are some limitations of this, of course. The retargeting can be imperfect, has to be done by an artist. This type of retargeting, depending on the complexity of the target face model, can take anywhere between 1 day to a couple of weeks. Of course, once the retargeting is done, the whole thing runs in real time. So depending on sort of how long you're planning on using this for, that could be worth the initial investment. But for lower tech solutions, a two-week investment can be sort of not feasible. So an automated approach could be better. So there's a number of trade-offs that you have to think about here. We made these types of trade-offs because we were primarily collaborating with Imagineers and animation artists at the Walt Disney Company who had that level of investment that they were willing to make. Yes?
So when they created this robot, they had the 7 kind of facial expressions in mind.
No,
to
no.
some extent, or they made it individually?
It was made independently. Yeah. All right, fun's over. Let's talk about some math. So I wanted to give an overview of this area of machine learning called learning reductions. For those of you who have taken complexity theory or algorithms, you've heard of things like complexity theoretic reductions, where you know, if you have one problem that you know is NP hard, and you could reduce this problem to another problem, you've proven that the other problem in polynomial time, you've proven that the other problem is also NP hard, right? And so there's some analogously, in some sense, we can think about things like learning reductions, where we convert one. Well, let me just go to the next slide. You know, we convert one problem to another problem, and then whatever error we get on the other problem, we can back convert that to the original problem, and show that, you know, ideally theoretically, if not in practice, that you know, this reduction preserves whatever guarantees you get in the reduced problem. So to rephrase what I just said, we know how to solve very quote-unquote standard machine learning problems, such as classification and regression. Lots of toolkits out there, many of the most popular ones in Python these days, you know, SVMs, such as regressions, deep learning, etc. Right? And we looked at a few quote-unquote more complex learning prediction problems, like variable length trajectories or edge prediction over a large image. And we saw how to reduce that down to a regression problem, right? A fixed size regression problem. The fixed size regression problem in this case is 150 variables in the speech animation example, which is still non-trivial, but something that you can solve on using a Python package, right? And then we showed how to you know, invert that reduction process to take this learned model on this simpler problem and apply it to the original problem, right? In some sense, right? So for example, if we get 100% accuracy or zero loss, zero regression loss in this reduced problem, right? Then you basically have perfect prediction on the original problem, right? That's an implication of this reduction. So there are a number of other learning reductions. Some of them are much simpler than this one, in order to sort of really analyze what's going on. And I will just look at one in detail for the remainder of this lecture, which is multi-class to binary. Okay? So multi-class classification is the problem where instead of having 2 classes to predict, you have some larger number, let's say 5 or 10 or whatever. And the goal is to train a model that can predict which of these k classes is correct, rather than which of these 2, right? And so the conventional approach for multi-class prediction is to do one versus all, right? We learn a scoring function per class, and then we predict the class with the highest score, right? This is a very straightforward generalization of the types of scoring function plus thresholding that we've looked at in class, where the scoring function is simply, where the threshold is basically plus or minus. Right? Some limitations of this generalization. It's linear in the number of classes, it's hard to prove generalization bounds, and so on and so forth. And so if we had a really strong theory about binary classification, can we just convert multi-class classification into a set of binary classification problems? Such that if we know that we can really learn these binary classifications well, and sometimes provably so, those guarantees lift to the multi-class setting. That's what a reduction is. Right. So here's the learning reduction recipe. This is fairly generic. You have your original training set, right? In this case, well, y is one of k discrete labels rather than binary. We're going to create a modified training set, or a set of modified training sets. In this case, we're going to reduce multi-class to binary, and so these labels are going to be 0 or 1, or plus 1 or minus 1. We're going to train our binary classifiers on these modified training sets, and then we have some recombination process. This is reversing the reduction. That gives us the original, gives us a classifier for the original problem. This is a general sort of setup. Any questions on that? Okay, so there are two flavors of ways of reasoning about these reductions. One is called an error reduction, which states that if the predictor in the reduced problem achieves epsilon loss in terms of classification error, right, then there's some implication in terms of classification error in the multi-class setting if there are k classes, right? And so, it's fairly straightforward to get something that's linear in k. So, as you get, as the error of the reduced problem converges to 0, then the error on the original problem will also converge to 0, albeit more inefficiently by a constant factor. Before, when I said, in the speech animation setting, if the reduced problem has 0 error, right, then the original problem has 0 error. If the reduced problem does not have 0 error, we don't have an analysis actually for the speech animation setting. And so here, we have an analysis that says that the error relationship decays smoothly, is a smooth relationship. Okay. Another style of reasoning about reductions is called a regret analysis. And so regret is defined not in terms of the absolute error, right, of your function class, but the difference between the error that your function class achieves versus the best possible error that your model achieves when you train on the data versus the best possible, right? And this quantity is, in some sense, only knowable in the limit of infinite training data, right? So this is more of a mathematical analysis type of thought experiment. In some cases, right, the problem could be very hard, and so the absolute error could be quite large, right? In particular, if the absolute error was higher than 1 over k minus 1, then this analysis is vacuous, right? We get error greater than 1, greater than 100%. But if you can show that you are performing close to the best possible model in your model class, then you can, for example, perhaps prove this type of regret, right? You're within a factor k of the regret you are in the multi-class setting is a factor k of the regret you get in the binary reduction, right? And so you can sort of, and this is this is also referred to as whether or not you have a consistent learning algorithm or an inconsistent learning algorithm or a realizable model class or unrealizable model class. So you have an inconsistent learning algorithm or one that can't achieve 0 error, then you always have this gap. Right, so just as I already alluded to this, in the sliding window regression setting, if the base model has 0 error, then the sliding window predictor has 0 error. If the base model has greater than 0 error, right, then what happens to the original prediction task? And the answer is we don't quite know, right? This is sort of an open question, a little little nice open question that we still haven't resolved yet. Okay, so let me just give you a little bit of detail about how to do this multi-class binary reduction in one approach. There are a few different approaches that people have proposed in the literature for doing this reduction. I'm just going to describe one. I'm describing this one because it's a fairly intuitive one to understand, right? So we have our original input x, and in this case we're doing 8-class classification, right? And what we're going to do is we're going to feed x into 4 binary classifiers, right? The first binary classifier is going to make a prediction: is x more likely to be class 1 or class 2? The second classifier is going to make a prediction: is x more likely to be class 3 or class 4? And so on and so forth, right? And then we're going to have, and then the predictions of these 4 classifiers get fed into the predictions of 2 more classifiers. So each of them is going to say, given this x, am I more likely? Is it more likely that the correct label is coming from this classifier or from this classifier? Given this x, this classifier tries to predict: is the correct label more likely to be coming from this classifier or this classifier? So we have like a decision tree of classifiers, if you will, right? And this is applied recursively until we get a prediction, right? And then the prediction basically it traverses the left-right decisions of these classifiers until we get to a leaf classifier that makes a prediction of 1 or 2 labels. And each of these is a binary classifier. Right? So let's talk about the learning reduction. So let's train this first layer, right? We need to create a training set for each of these 4 binary classifiers in the first layer, right? And so the training set will look as follows. We'll always have the original x, the original input, right? And then we'll have a binary label. Recall that the labels all have to be binary. In this case, I'll just write the binary labels as 0 or 1. You could always remap that to +1 or -1 if that's more mathematically convenient for you. And this applies for all training examples in the original training set where the true label was one of these 2, right? So for training this guy, the true label has to be, we're going to create a training set where the true label is one of class 1 or class 2. Okay? And after we create these 4 training sets, we're going to train these 4 classifiers. And then we're going to freeze them. And then for the second layer, we're going to create another set of converted training sets. So here, we again have the original input x, and then we have a binary indicator label of 1 corresponding, I guess, to left or right, as you wish. In terms of which one's correct, and we're only going to construct this training set over inputs x from the original training set, where the original label belongs to one of the 4 possible classes that this classifier is predicting over, and this is an example where the 2 classifiers in the first level did not make a mistake, right? So if the true label was 1 for this example, then H12 must have made the correct prediction. It doesn't really matter what H32 predicted, but H12 must have made a correct prediction. Otherwise, we throw this example out and don't include it in this training set. Yes?
What is the Y in LR for the,
Oh, so like 1 if, the label is, it depends on how you define it. It's 1 if you're going to go this way, and it's 0 if you're going to go this way. And then this process is applied recursively. Okay. So the classification problem at every layer, right, depends on what the performance of the previous layers, right? So if you train this guy and it makes some mistakes, then those examples are thrown out and not put into the training set of this classifier, right? So this is, in some sense, we have an adaptive learning reduction. We create a sequence of learning reductions. Each one is actually adaptive to the results of the learning problem applied to the previous learning reduction. Right. And so recall that there are two flavors of analysis here, right? We have an error reduction and then we have a regret reduction, right? So for this algorithm, which is called the filter tree, if each binary classifier, it has regret upper bounded by R, right? Then you could show that the filter tree has multi-class regret, the regret of the original problem, upper bounded by log base 2 times k, which is the number of classes times R. Right? This is a pretty good dependence on k, right? And the reason, of course, is that if you don't make a mistake, you don't make a mistake, you don't make a mistake. You only need to not make a mistake log k number of times for any individual exam. If you're interested in the details, I only explained the high-level intuition, of course. If you're interested in the details of the analysis, they're available in this paper. Yes?
Would it be possible to have a situation where, like, one would win over two, two wins over three, three wins over one? It depends on which.
So, right. So that's not possible with this partitioning. It is possible in general, yes. But and that's one of the reasons why the authors of this paper defined this. Okay. So some other benefits of this approach. At runtime, it's logarithmic with respect to the number of classes, right? If you had, let's say 1,000 classes that you're predicting over, a one versus all model that creates a score for each of those 1,000 classes and then chooses the class that has the highest score has running time linear in 1,000. Whereas here, at test time, it's logarithmic in 1,000, right? Because if you call this classifier and this classifier predicts left, you don't need to run any of these guys, right? The analysis assumes that you've done it, you have, but in practice, you don't need to. Any questions on that? Yes?
How do you know whether it's left or right if you don't know the results of the previous parts of the tree?
Because you trained it. The training, right? The training was top down. At test time, you're doing bottom up.
Okay.
Right? The training set, right? When you're training this guy, first you train these guys, right? And from the perspective of this guy, right? All you're trying to do is try to predict for the examples where the true label was either 7 or 8 to try to make the right prediction. And then you froze this layer, right? And then you train this guy that took the predictions of these guys that were not wrong, and you create a training set that says, I want to make the right prediction. So so these are already trained. And then at test time, everything's already trained, so then we just actually call it bottom up, in which case you could do it lazily, right? You don't need to call these classifiers if this guy predicts left.
Yeah, right. So like left and right here, after you create it, would have actual numbers in there.
Yeah, it was a binary classifier. Like you would say left was +1 or right was -1 or vice versa. However you define the training set. Yes?
What's the reason for throwing out the data from the training set of successive layers if they're misclassified in previous layers?
You don't want to double count mistakes.
Okay.
Yeah. So did I make a mistake? Yes or no? Did I make a mistake? Yes or no? Did I make a mistake? Yes or no? Right. If I'm going to make a mistake here, I don't want to include it in the training sets of here or here because I'm going to double count it or triple count it. Right. You're going to make a mistake anyways. You're going to only count it once. So in some sense, this model has undefined behavior in terms of the analysis, right? Because it wasn't included in the training set, right? So it's going to make an arbitrary prediction on this example, left or right. But even if it made the right prediction, this guy's going to get it wrong anyways. So you might as well just not even include it in the training set here. In the analysis, what that means is you're not double counting or triple counting mistakes. Yes?
If you have a number of classes not equal to the power of 2, then it wouldn't be perfectly balanced.
Oh, that doesn't matter. Yeah, it's fine. Yeah, it doesn't need to be perfectly balanced. Yes?
So do each of those smaller models need to be smaller than one big model you use for multi-class classification to get?
Yeah, so that's right. So because these training sets are smaller, right? One question is generalization, overfitting. And that is not, and I just sort of ignore that issue here, right? And so the answer is yes in practice, yeah. Yes? Yeah, so it's assuming that for every example, there's a single correct class out of k classes, right? So like, if I give you a word, is it a noun or a verb or whatever?
But if you had something that had overlapping classes?
Then you'd have to, that's called multi-label prediction.
Yeah.
This is multi-class prediction, where this is only a single label.
Like, if you separate class, but they have neutral labels, is that still okay?
That's multi-label prediction, where you're predicting more than one label at a time. Here you're only predicting a single label, is just one of k discrete classes. It's a different prediction task. I personally am a big fan of learning reductions. I feel like in this day and age of deep learning, where you can create these complicated systems, think about how to break apart these complicated systems into individual modules, and then reason at a high level about the interactions between the modules, without worrying about how to train these modules, which we would just train using deep learning. It gives us a very nice handle in terms of reasoning about the capabilities of a complicated system at a fairly high level of abstraction, just under the assumption that these modules are learnable. And so a lot of the research in my group focuses on using learning reductions in a variety of ways. A bit more complicated than what you saw in class today, but nonetheless of a similar flavor. So if that's something that interests you, you're welcome to check out some more of the papers on my website. Next week, we'll be looking at unsupervised learning and data visualization. That's it.